Hello friends, welcome to the applied polymer rheology. Here we are going to discuss about the fluid behavior. Now in this particular segment we are going to discuss about the Newtonian and simple non-Newtonian fluids, complex non-Newtonian fluids, fluids influenced by the external force fluids, non-continuous fluids. We are going to discuss about the relativistic fluids. Now let's talk about the rheology. The basic introduction. The rheology term is used to examine the flow and deformation of all matters, both solid and fluids. The key to understanding polymer processing is provided by the rheology. The structure and characteristics can be related, like here you can see in this aspect. Additionally, the flow and deformation, they are the part of every polymer processing procedure. Now, rheology can be divided into two aspects. One is the solid and second one is the fluid. Now, when we talk about the solid, there may be two type of solids. One is the rigid solid, where you cannot change the shape, and second one is the deformable solids, where you can easily change the shapes. They may acquire or they don't acquire the original shape. Now, if we talk about the deformable solids, thereby these can be further subdivided into two categories. Elastic solid, usually attributed to the Hookean solid, and non-linear solids. Now, if we talk about the fluids, there are two types of fluids. One is the ideal fluid and second one is the viscous fluid. So, if we talk about the viscous fluids, again this can be subdivided in two different aspects. One is the non-Newtonian fluid and second one is the Newtonian fluid. So, let us talk about the Newtonian liquid model or Newtonian fluids. These Newtonian liquids are a type of a fluid that exhibits a linear relationship between the shear stress and shear rate. Now, shear stress, sometimes referred as a tau, is the force per unit area applied parallel to the surface of the liquid, while shear rate, sometimes referred as du or dy, this represents the velocity gradient perpendicular to the direction of flow. The equation that describes the relationship between the shear stress and the shear rate is known as Newton's law of viscosity, and mathematically it can be represented as tau is equal to the mu into du over dy, where tau is the shear stress and mu is the dynamic viscosity and du over dy is the shear rate. The dynamic viscosity mu, this represents the resistance of the liquid to flow, and it is a measure of the internal friction. So, whenever liquid flows, then there is some resistance attributed within the liquid and within the surface. So, this mu represents the resistance of liquid to flow. A high viscosity, this indicates the thicker or more resistant fluid, while a lower viscosity implies a thinner or less resistant fluid. The unit of dynamic viscosity is typically expressed in Pascal second or PAS or poise. The Newtonian liquid model, this assumes that the dynamic viscosity remains constant regardless of the shear rate applied. This implies the liquid's flow behavior is independent of the applied stress and deformation rate. The shear rate du or dy can be calculated by dividing the velocity difference between the two fluid layers. Like here, these are the two fluid layers. So, the velocity difference between the two fluid layers by the distance between those layers. So, this is this one. Now, let us talk about the Newtonian liquid model, in which the consider a fluid layer. This is the fluid is flowing in this particular direction. Now, consider a fluid layer with a height h and width w between the two plates, and these two plates are parallel in nature. The top plate is moving with a velocity v1, while the bottom plate is stationary with the velocity v is equal to 0, v2 is equal to 0. The shear rate du or dy is the velocity gradient between the two plates, which can be approximated as v1 minus v2 over h. The shear stress tau is the force required to maintain relative motion of the plates, which is proportional to the applied force and inversely proportional to the area of the contact. Therefore, tau is proportional to F over A. Now, but if we rearrange the terms and considering the definition of the viscosity, we get tau is equal to mu into du or dy, which is the Newton's law of viscosity. Let us talk about the simple non-Newtonian things. The simple non-Newtonian fluids, they are those fluids whose flow behavior is affected by the rate of shear. Now, shear thinning, the fluid becomes the less resistant to the flow as applied force or shear rate is increased. Now, shear thickening, the fluid becomes more resistant to flow as the applied force or shear rate is increased. So, this is the shear thickening, and this becomes the simple non-Newtonian fluid. Now, here if you see that this particular figure, the shear stress versus shear rate comparison for a Newtonian, shear thinning and shear thickening fluid. This one is the shear thickening fluid. So, this B and C, they are the simple non-Newtonian, and shear thinning fluid B, this one, are also called the pseudoplastic, and shear thickening fluid, they are termed as dilatant. Now, this particular figure, this is the logarithm of apparent viscosity versus logarithmic of shear rate of Newtonian, shear thinning and shear thickening fluids. So, if we rewrite the Newton's law of viscosity to get the apparent viscosity, sometimes referred as mu apparent, this is equal to tau yx is equal to minus mu apparent dvx over dy, and we get mu apparent as tau yx over dvx over dy, and mu apparent for a Newtonian is a constant. Now, shear thinning fluids show a decreasing apparent viscosity with increasing shear rate, and shear thickening fluid, this shows an increasing apparent viscosity with an increasing shear rate. Now, simple non-Newtonian, these can be expressed in another form using Ostwald-de power law, and this is tau yx is equal to minus k dvx over dy to the power n minus 1 over dvx over dy, where dvx over dy is the absolute value of the rate of shear, and k is a consistency index, and eta n is the flow behavior index, this one. So, if we write the above expression in the form of tau yx is equal to k dy over dt to the power n, where dy over dt is the rate of strain, and dy over dt is equal to minus dvx over dy. Now, this law applies only when log tau ix versus log d over dt plot a straight line. Now, n is the slope of each plot, and the existence of shear thinning or a shear thickening behavior in the material depends on the composition and interaction between its constituents. Now, you see that the ketchup is a non-Newtonian fluid. It does not follow the rules. Now, if we have in this particular table, we have enlisted different type of fluids with the n values with some simple examples. Like if we talk about the shear thinning fluids, the n is less than 1, and the examples of polymer solutions, polymer melts, foods, all those things. Then Newtonian, n is equal to 1, they are water and organic fluids, they are the best examples. Then shear thickening, where n is greater than 1, they are the continuous and dispersed phases, water, sand, cement, water, corn, starch, etc. Let us talk about the complex non-Newtonian fluids. Now, the complex non-Newtonian fluids are subset of non-Newtonian fluids, and that exhibits more intricate rheological behavior beyond simple shear thinning or shear thickening. These fluids often possesses a combination of different flow characteristics, making their flow behavior more complex and different or difficult to model compared to the Newtonian fluid. Now, the complex non-Newtonian fluid, they find application in various fields. This includes the material science, chemical engineering, food processing, pharmaceutical and cosmetics. The complex non-Newtonian fluid exhibit time parameter as an influencing factor, it means that they change their properties with respect to the time, and this can be expressed as tau is equal to phi dy over dt and t. Now, there are various type of a complex non-Newtonian fluids, each with its own unique characteristics. Some of the common examples of these complex non-Newtonian fluids, the shear thinning fluid. These fluids are also known as the pseudoplastic fluids. They exhibit the decrease in the viscosity with increase in shear rate. As the shear rate increases, the fluid's resistance to flow decreases and resulting in thinner consistency. The example of shear thinning fluids, this includes the ketchup, toothpaste, certain type of paints. When these fluids are at rest, they have higher viscosities, but they flow more easily when subjected to shear stress. Then shear thickening fluids. In contrast to shear thinning fluids, the shear thickening fluids, also known as the dilatant fluids, experiences an increase in viscosity with increasing in shear rate. And these fluids become thicker and resist flow when subjected to higher shear rates. Silly putty and a mixture of cornstarch and water, sometimes called as obec, they are the example of shear thickening fluids. Bingham plastic fluids. Bingham plastic fluids such have a yield fluids have a yield stress, meaning that they require a certain amount of applied stress before they start to flow. Once the yield stress is exceeded, these fluids exhibits linear viscous behavior similar to the Newtonian fluid. Common example of Bingham plastic fluid includes the certain type of drilling mud, mayonnaise, tomato sauce, etc. Then thixotropic fluids. The thixotropic fluids exhibits a time dependent decrease in viscosity when subjected to continuous shear stress. With prolonged shear stress, the fluid gradually becomes less viscous and flows more easily. However, when the shear stress is removed, the fluid recovers its original viscosity over time. Some paints, gels, and certain printing ink displays thixotropic behavior. Rheopactic fluids. The rheopactic fluids behave opposite to the thixotropic fluids, and they exhibit a time dependent increase in viscosity under continuous shear stress. The longer the shear stress is applied, the more viscous the fluid becomes. However, once the shear stress is removed, the fluid gradually returns to its original viscosity. Some clay suspensions, certain lubricants, they exhibit the rheopactic behavior. While considering the complex non-Newtonian fluids, let's discuss about some related models like power law model. The power law model is a commonly used mathematical expression for describing non-Newtonian fluid. It relates the shear stress tau to the shear rate gamma through a power law relationship. Now, this is represented mathematically like this, where this K is the consistency index and is the flow behavior index, and the consistency index represents the fluid's resistance to flow, and the flow behavior index indicates the degree of shear thinning, and usually n is less than 1, or the shear thickening when n is greater than 1. The Herschel-Berkeley model. The Herschel-Berkeley model, this extends the power law model by including a yield stress tau naught, which represents the minimum stress required for the fluid to start flowing. The relationship between the shear stress tau and shear rate gamma is given by this particular relationship. Now, this model captures the behavior of fluids that require a certain amount of force to initiate flow. Bingham plastic model. The Bingham plastic model, this describes the fluids that exhibit a yield stress but have a linear relationship between the shear stress tau and a shear rate gamma. Once the yield stress is exceeded, the model can be expressed like this, where the tau naught is the yield stress and mu naught is the plastic viscosity. The fluid behaves as a rigid solid below the yield stress and as a Newtonian fluid above the yield stress. The Casson model. The Casson model is used to describe the behavior of fluid with a yield stress and a non-zero yield strain. It relates the square root of the shear stress tau to the square root of the shear rate. Now, this can be represented mathematically like this, where the tau naught is the yield stress, and mu naught is the plastic viscosity. This model accounts for the non-linear relationship between the stress and strain in yield stress flow. Now here let us talk about the complex non-Newtonian model. This is the rheological phenomena of a complex non-Newtonian fluid, where we can have the thixotropic behavior, viscoelasticity behavior, and the yield stress and the time dependent behavior. Now let us talk about the viscoelasticity. Now for understanding the viscoelasticity model, we need to understand the non-Newtonian liquid model, which is represented over here. Here the delta x between the two layers, and the ideal elastic solid, that is the Hookean model, which is represented over here. Now this particular figure shows the Newtonian liquid or a dashpot. This shows the elongational deformation along the x-axis, the dashpot. This can also be used as a shear deformation. This can be written as xi is equal to delta x over h. This figure shows the deformation is the time dependent. In a Newtonian fluid, the relationship between the time and deformation is a linear. So we can express the shear strain rate as gamma xy is equal to gamma xy delta t. The linear elasticity or the Hookean spring, the force F is directly proportional to the deflection, that is delta x. So F is equal to k delta x. K is the constant of proportionality or spring constant, and this is the schematic representation of the Hookean solid. Now this equation can be expressed as the following in terms of stress and strain. Tau yx is equal to gamma g gamma xy, and tau yx is the shear strain and gamma xy is the corresponding shear strain. Now the spring, this depicts the body that is stretching, but it can also be used to depict the shear. As soon as the load is applied, the spring deforms, and this deformation lasts as long as the load does. At time delta t, when the load is relieved, the material element will almost immediately take onto its original shape. James Clerk Maxwell, he developed the viscoelastic model initially, and he presented a system model that incorporates the elastic and viscous effects. The Maxwellian model of today, which is graphically represented by instantaneous change in the spring and a time dependent reaction, this is based on this model and the linear differential equation that or relates the stress and strain. So the Maxwell model and White model, they are the viscoelastic model. Now this particular figure, this shows the characteristics of both the Newtonian fluid and elastic fluid. Now here you see the difference between the Maxwellian model and White model. This is the viscoelastic model of elastic and Newtonian, and this one is the ideal elastic solid spring and Newtonian, that is Newtonian liquid, that is a dashpot. So here you see the difference. So both viscous, that is a resistance to flow, and elastic, that is ability to recover from any kind of deformation, these qualities are present in these fluids. So when subjected to an applied stress or deformation, they exhibit both instantaneous elastic responses and time dependent viscous responses. Gels, polymer solutions, various biological fluids, they are the best example of viscoelastic fluids. Now here we are going to discuss about the Maxwellian model. This is the schematic representation of the viscoelastic Maxwellian model. Here this is the T, and then if we stretch the spring, then it can be represented as T plus delta T. Now stress tau xy is applied to the system. Now stress is same in both the fluids. Stress usually is same in both the fluids and a solid element. total strain is the sum of elastic strain, that is gamma xyg, and the viscous strain xyn. So tau xy is equal to tau xyn is equal to tau xy g. This is, let us say, equation A, and gamma xy is equal to gamma xyg plus gamma xyn. This is, let us say, equation number B. Now, if we take this, this is the viscosity of liquid. So tau xy gamma xy bar, that is the Newton's law, and tau xy is equal to g xy, that is Hooke's law, and g is the modulus of rigidity. So if we differentiate this equation, that is equation number B, it becomes is equal to so if we combine equation A, B and E with equations C and D, so it becomes d tau xy dt is equal to g gamma xy dt minus tau xy lambda, where lambda is equal to g over. Let us talk about the thixotropy. Now, this thixotropic fluid, they demonstrate a time-dependent decrease in viscosity when subjected to continuous shear stress. Now, this implies that the fluid's viscosity reduces when it is repeatedly stirred out shear. Now, this is represents the thixotropic fluid behavior. This is plotted with the shear stress versus rate of shear, and this is the time dependent model. Now, however, when fluid eventually regains its initial viscosity after the shear stress is eliminated, so the various paints, gels, adhesive, they frequently contain the thixotropic fluids. Now, these fluids can be thought of as a fluid in which tau is equal to phi d gamma over dt in T. This is the thixotropic fluid behavior, where eta is the initial viscosity and eta infinity is the viscosity after infinite time. So, this is the generalized graph rate of shear versus apparent viscosity. Now, let us talk about the yield stress and time dependent behavior. The yield stress, these fluids have a threshold stress known as the yield stress, and that must be exceeded before they start to flow. And these fluids behaves as a solid or remain static below the yield stress. There are some of the examples which we have enlisted, like blood, toothpaste, crude oil, creamy fluids, gels, foams. All these things are the example of yield stress fluids. They decrease the viscosity and start the flow once the yield stress is exceeded. So, toothpaste, mayonnaise, certain colloidal suspensions, they are again the best example of yield stress fluids. Now, fluids influenced by external force field. The electrically conducting field play a very important role in rheology. Stress is a function of strain and applied electrical field and can be expressed as tau is equal to the phi d gamma over dt field. The example includes the magnetohydrodynamics, originally applied to a situation involving the plasmas and ionized gas. Their viscosity profile behavior is comparable to that of the simple and non-Newtonian. Let us talk about the non-continuum fluid. Non-continuum fluids, also known as the rarefied gases, rarefied fluids or constant gas. These refer to which in which the mean free path of the molecule is comparable to or a larger than the characteristic length of the fluid. Unlike continuum fluids such as liquids and gases at standard conditions, non-continuum fluids exhibits behavior that cannot be described by the classical fluid dynamics equation such as Navier-Stokes equation. Instead, their behavior is governed by the statistical mechanics and kinetic theory. Fogs, aerosols, spray, smoke, rarefied gases, they are the example of non-continuum fluids. In this regime, the Navier-Stokes equation, which are the cornerstone of classified fluid dynamics, are no longer valid. There are some key points about the non-continuum fluids like mean free path. In non-continuum fluids, the average distance a molecule can travel without controlling with another molecule, this is covered as a mean free path, is significant compared to the size of the system. Now, this implies that the molecular collision between becomes less frequent and individual molecular behavior becomes important. Constant number. This number defined as the ratio of the mean free path to the characteristic length scale of the system and is used to characterize the non-continuum behavior. When the constant number is large, Kn is greater than 0.01, the fluid is considered as a non-continuum. The molecular interaction. In non-continuum fluids, molecular interaction becomes more and more significant, and the behavior of individual molecules such as their collision, diffusion and thermal effects cannot be ignored. Departure from continuum assumptions. The continuum assumptions such as no slip boundaries or no slip boundary condition and the assumption of local equilibrium break down in non-continuum fluids. The fluid may exhibit slip flow where the velocity at the boundary differs from the that of the predicted by the no slip conditions. Rarefaction effects. The rarefaction effects become prominent in non-continuum fluid, and these effects arise due to the low density of molecule and can include thermal creep, pressure driven flow and velocity slips. Constant paradox. The non-continuum fluid behavior can often contradict the predictions of classical fluid mechanics. For example, in micro scale or in nano scale channels, the flow rate may increase with a decreasing pressure gradient and contrary to the behavior observed in the continuum fluid. The modeling approaches. To describe the non-continuum fluid behavior, various modeling approaches are used like Boltzmann equation, direct simulation Monte Carlo methods, molecular dynamic simulations, and these methods account for individual molecular interaction and provide insights into the non-continuum phenomena. The various applications are attributed. The non-continuum fluid dynamics is relevant in many engineering and scientific applications. This includes the microfluidics, vacuum system, gas flow in the non-porous material, spacecraft re-entry and rarefied gas dynamics. Understanding the flow behavior of non-continuum fluid is essential for designing efficient processing techniques such as extrusion, injection molding and a film casting to achieve the desired polymeric product properties. The non-continuum fluids in polymer rheology, they are also used in study phenomena such as polymer melt spinning, fiber formation and the behavior of polymer blends and composites. The characterization of these non-continuum fluids involves the measuring properties like viscosity, shear stress, shear rate, viscoelastic properties using techniques such as rotational rheometry, capillary rheometry and dynamic mechanical analysis, or sometimes referred as a DMA. Let us talk about the relativistic fluids, the branch of fluid dynamics that deals with the behavior of the fluids at relativistic speed, where the velocity approaches to the speed of light. The relativistic dynamics modifies the equation of classical fluid dynamics such as conservation equation of mass, momentum and energy by incorporating the Lorentz transformation and relativistic energy momentum relations. The relativistic fluids, this exhibits the unique properties and phenomena compared to their non-relativistic counterparts. For example, energy and mass are interconvertible. The relativistic energy momentum relation E is equal to mc square. This allows the conversion of mass into energy and vice versa, and the enhanced particle velocities. The enhanced particle velocities, the relativistic effects allow the particles within the fluid to achieve the velocities approaching to the speed of light. resulting the relativistic shocks and generation of particle jets. The relativistic temperature, the concept of the temperature in the relativistic hydrodynamics is modified to count the relativistic energy and momentum. This led to the different thermodynamic properties and equation of a state. So, dear friends, in this particular segment, we discussed several rheological models, rheological approaches, which are very much useful in the polymeric system, especially when we go for any kind of molding operation, injection, whether injection molding or a compression molding operation. And for your convenience, we have enlisted several references which you can utilize as per your requirement. Thank you very much.